Welcome back to Key Safety Talks.
Oh
Today we're tackling a subject that's way more interesting than it might sound at first.
yeah.
The world of mechanics and structures.
It's one of those things we don't think about much until something goes wrong. Right.
Yeah.
But honestly, understanding how forces work on different materials is key to keeping ourselves safe.
Yeah.
Whether we're talking about massive bridges
Ugh.
or just everyday objects around the house.
Okay.
That's a good point.
It's easy to take for granted how much engineering goes into simply making sure a roof stays over our heads.
Yeah.
And speaking of things going wrong,
Right.
I was struck while reading through the material just how many accidents happen
Yeah.
because something was overloaded
Oh, yeah.
or a material just couldn't take the force applied to it.
Right. It's often like a mismatch, you know?
Yeah.
Either the design didn't account for the kinds of forces that would be acting on it, or the material itself wasn't up to the task.
That makes sense.
Yeah.
The source material had this example of a 50-pound force
Okay.
applied to glass versus wood.
Oh, yeah.
Of course, the glass shatters,
Right.
but the wood is likely fine.
Yeah.
I guess it's not just about the amount of force,
Right.
but how it's spread out.
Exactly. The glass example
Yeah.
is a perfect illustration of force distribution.
Okay.
A concentrated force on a small area is much more likely to cause damage than the same force spread over a larger area.
So it's like stepping on a nail versus standing flat-footed on the floor.
Right.
Same weight, totally different outcome.
Exactly.
Okay.
And that brings us to the concept of stress,
Okay.
which is basically force per unit area.
Okay.
It's all about how intensely that force is applied to the material.
Okay, so force is the overall push or pull.
Right.
And stress is how that force is focused on a specific spot.
That's a great way to put it.
Oh.
And understanding stress distribution is crucial for figuring out whether a material is strong enough for its job.
Right.
It's why engineers spend so much time analyzing things like load paths and potential points of failure.
And why regular maintenance is so important, too.
Oh, absolutely.
I mean, the source material mentioned a worker falling through a plastic skylight
Oh, wow.
that had degraded over time from UV exposure.
Yeah.
That's terrifying.
Absolutely.
Yeah.
Materials don't stay the same forever.
Right.
They can weaken over time due to sunlight, corrosion, wear and tear, you name it.
Yeah.
Ignoring this is how those freak accidents actually happen.
Makes you wonder what else around us is slowly getting weaker without us knowing.
Right.
Okay, so we got force, stress,
right.
and then there's this thing called the safety factor.
Right.
Which seems like a really important concept.
Safety factors are crucial. It's basically building in a buffer.
Yeah.
Because in the real world,
Right.
you can't predict every single force or event
Right.
that might act on a structure.
Yeah.
Engineers use safety factors to make sure things can handle more than they're expected to handle.
So it's like packing extra snacks for a hike.
Yeah.
You might not need them,
Exactly.
but it's better to be safe than sorry.
Right.
But how do they actually determine what safety factor to use?
Yeah.
They can't just be random, right?
It's definitely not random. There's an equation for it.
Okay.
But basically, you look at the load that would cause something to fail and then factor in how much stress the material can actually handle.
Okay.
That ratio becomes your safety factor.
That makes sense.
Right.
And speaking of things failing dramatically, the Hyatt Regency walkway collapse is a stark reminder of how important those safety factors and good design in general really are.
Absolutely.
Yeah.
That tragedy stemmed from design errors, particularly in how the load was distributed.
Yeah.
It's a sobering lesson
Right.
that even seemingly small oversights can have catastrophic consequences.
So we've talked about forces acting on materials
Right.
and how they can lead to stress, but the source material also delves into all these different ways things can fail.
Oh.
It's not just snapping in half.
Yeah.
There's tension,
Right.
compression, bending,
Yeah.
torsion, the whole vocabulary list.
Each of those terms describes a different way materials respond to force. Tension is like pulling on a rope. Compression is pushing down on a spring. Bending is, well, like bending a ruler. And torsion is twisting, like wringing out a wet towel.
Okay, I'm starting to get the picture.
Okay.
But how does this actually play out in real-world disasters?
Right.
Do we have examples for each of these?
We do.
Yep.
Think of a cable snapping under tension or a pillar crumbling under compression.
Right.
Bending.
Yeah.
That's how bridges collapse if they're not properly supported.
Right.
And torsion.
Yeah.
Imagine a twisting force causing a ladder to buckle.
That's helpful.
Right.
It's giving me some unsettling mental images, though.
I bet.
And then there's fatigue.
Yeah.
Which I think we can all relate to on some level.
Right.
Except for materials, it's not about needing a nap, right?
Exactly.
Okay.
Material fatigue is about repeated stress, weakening something over time.
Right.
Even if each individual stress is below its breaking point.
Okay.
Think of bending a paperclip back and forth.
Right.
Eventually, it breaks.
And those seemingly small breaks can have huge consequences, right?
Absolutely.
Like that DC-10 crash in 1979.
Right.
The source material mentions a tiny bolt failing from fatigue.
Oh, wow.
Which ripped through hydraulic lines.
Yeah.
And led to a complete loss of control.
That's a tragic example of how crucial it is to understand fatigue and design for it.
Yeah.
Especially in things like airplanes and bridges that experience constant stress cycles.
Yeah.
Even small components can be critical points of failure.
Right, like that United Airlines incident in 1989.
Oh, right.
Where a DC-10 lost hydraulic control when a piece of its engine broke off.
Wow.
It highlights how dynamic forces can cause damage in an instant.
Right.
Luckily, they managed to land safely in that case.
Yeah, that's good.
So we've covered how forces affect materials and the various ways things can fail.
Right.
But what actually causes these structural failures in the first place?
Well, there are a few usual suspects.
Okay.
Design errors are a big one.
Okay.
Which can be anything from incorrect assumptions to poor material choices, like using salt instead of sugar in a cake recipe.
Right.
The end result isn't going to be good.
Or trying to build a house with bricks that crumble in your hand.
Yeah.
Not a recipe for success.
Exactly. Then you have issues with the materials themselves.
Okay.
Maybe there are inconsistencies in their properties, or they've degraded over time.
Yeah.
And of course, physical damage plays a role. Like when a structure is hit by a car or something unexpected happens, it's life throwing a wrench into the plans, so to speak.
And then there's poor workmanship.
Right.
Where maybe corners were cut during construction or things weren't assembled correctly. I'm picturing putting together furniture with missing screws. That's not going to end well.
You're definitely going to end up with a wobbly situation.
Right.
And finally, there's overloading.
Okay.
Which is when a structure is simply asked to bear more weight than it was designed for. Like trying to fit 10 pounds of potatoes in a 5-pound bag.
Right.
Something has to give.
And that give is what makes the news, unfortunately.
Right.
The source material talks about how even a change in use can lead to overloading. Like a roof designed for people being converted into parking.
Right.
Yeah.
It's crucial to consider not just the original purpose of a structure,
but
also how it might be used in the future.
Right.
Adaptability is key.
Speaking of adaptability,
the
source material also dives into the unpredictable world of earthquakes.
Right.
I have to admit, reading about liquefaction was a bit unsettling.
Oh, yeah.
It's like the ground turning into quicksand.
It's a fascinating, albeit terrifying phenomenon.
Right.
Essentially, when water-saturated soil is shaken during an earthquake, it can lose its strength and behave like a liquid, causing buildings to sink or tilt.
The Christchurch earthquake in 2011 is a stark example of the damage liquefaction can cause.
Right.
It really emphasizes how important it is to understand these geological factors when designing structures in earthquake-prone areas.
Absolutely. It's not just about the building itself, but what it's built on.
Right. A comprehensive understanding of soil mechanics and earthquake impacts is essential for creating truly resilient structures. It really highlights the interconnectedness of different engineering fields. You can't just design a building in isolation. You have to consider the soil, the climate, and potential hazards like earthquakes.
It's like this giant puzzle where every piece has to fit together perfectly.
Right.
And speaking of fitting together, the source material also really emphasizes the importance of communication.
Oh, absolutely.
Between designers and builders.
Yeah.
It sounds like a breakdown in communication can be just as dangerous as a faulty material.
Absolutely.
Wow.
A brilliant design is useless if the people building it don't understand it.
Right.
or if there are mistakes during construction.
Right.
Clear communication, shared understanding, and attention to detail are all It's kind of like those pre-flight checklists pilots use.
Right.
Right. They're not just going through the motions.
Yeah.
They're making sure every critical step is taken to ensure a safe flight.
That's a great analogy.
Okay.
It's about creating a culture of safety.
Yeah.
Where everyone involved understands the importance of their role and how even small mistakes can have consequences.
That makes a lot of sense.
Right.
So we've talked a lot about the big picture of mechanics and structures.
Right.
But the source material also goes into some more specific applications.
Right.
I have to admit, some of those equations for things like welds and fluid mechanics made my head spin a little.
Those equations can definitely look intimidating.
Yeah.
But at their core, they're really just expressing the relationships between forces, motion, and the properties of materials.
Okay.
Once you understand those relationships, you can start to predict how things will behave in different situations.
So it's like having a secret decoder ring for the physical world.
Exactly.
You can figure out how much weight a weld can handle or the pressure a fluid exerts on a surface.
And speaking of decoding the physical world, I thought the section on soil mechanics was particularly fascinating.
Okay.
It turns out there's a whole lot of science behind how soil behaves under pressure.
It's easy to take the ground beneath our feet for granted.
Right.
But like you said earlier, what a structure is built on is just as important as the structure itself.
Absolutely.
There's that saying, the strength of a building lies in its foundation.
Right. That's a perfect analogy. The type of soil, its moisture content, even how it's compacted, can all affect a structure's ability to withstand loads and resist settling.
Yeah.
A good design starts with understanding the ground it's built on.
Okay. That makes sense.
Right.
And that brings us to retaining walls, which I always thought were just there to make landscaping look nice.
Oh, yeah.
But they actually have a really important job.
Yeah. Retaining walls are essential when you're dealing with changes in elevation.
Right.
They're designed to hold back soil or rock and prevent things like landslides. And erosion.
Right.
It's basically an engineering solution.
Okay.
To the constant force of gravity trying to pull everything downhill.
It's like a silent battle. Between nature and engineering.
Exactly.
With the retaining wall acting as a barrier.
And to win that battle, engineers need to understand things.
Okay.
Like the angle of repose.
Okay.
The steepest angle at which a slope will remain stable.
Right.
It's a delicate balance between gravity and the friction holding the soil together.
So it's not just about building a wall.
Right.
It's about understanding the forces that are constantly acting on it.
Right.
It's making me look at hillsides a little differently now.
Yeah. It's all about understanding how forces interact, right?
Right.
Now, shifting gears a bit, the source material also talks about beams, which are those horizontal structural elements you see everywhere.
Right.
They're kind of like the backbone of a building, wouldn't you say?
They do seem pretty essential.
Yeah.
I mean, they're what hold up roofs and floors.
Right.
But I never really thought about how they actually work.
Yeah.
How do they manage to support so much weight?
Right.
Without just snapping in half.
Beams are all about transferring loads.
Right.
They take the weight from roofs, floors, and other parts of the structure and channel it down to the foundation.
Okay.
And the key to their strength lies in their shape and the material they're made from.
So it's not just about using the strongest material possible.
Right.
The design of the beam is just as important.
Exactly. Engineers have to carefully calculate the stresses and deflections that will occur under different loads.
Right.
They need to make sure the beam is strong enough to resist bending and shearing forces.
It's kind of like watching a tightrope walker gracefully balancing on a thin wire.
Right.
Right.
Yeah.
It seems impossible.
Yeah.
But there's a lot of science and careful calculation behind it.
That's a great way to put it.
Okay.
And then we have columns.
Okay.
Which are like the vertical counterparts to beams.
Yeah.
They're what hold up the roof
right.
and prevent everything from collapsing inwards.
It's like they're carrying the weight of the world on their shoulders.
Right.
But why are they often those distinctive shapes, like I-beams or cylinders?
Right.
Is that just for aesthetics?
It's all about maximizing strength and stability.
Okay.
The shape of a column is crucial for preventing buckling. which is when a column suddenly becomes unstable and collapses.
So it's like trying to balance a broom handle vertically. It's prone to toppling over, right?
Right.
But those I-beam shapes are much more resistant to that kind of instability.
Exactly. And speaking of understanding when a column might reach its breaking point, the source material mentions something called Euler's formula.
Okay, I have to admit, that one went over my head a bit.
Oh, okay.
Is it something I should be worried about when walking under columns?
Don't worry, engineers have you covered.
Okay.
Euler's formula is a mathematical expression that helps them predict the critical load at which a column will buckle. It takes into account things like the column's length, the material's stiffness, and how it's supported.
So it's like having a crystal ball.
In a way, yes. It's a tool that helps them design columns that are strong and stable enough to support the loads they're expected to carry.
That's reassuring.
Right.
But it seems like even with all these calculations and formulas, there's still a chance that things can go wrong.
You're right. Right. That's why the source material emphasizes the importance of considering multiple modes of failure when designing any structure. Engineers can't just assume a structure will fail in one predictable way. They have to think about all the possibilities, bending, buckling, shearing fatigue, or any combination of these.
So it's like playing chess.
Exactly.
Where you have to anticipate your opponent's every move.
It's about creating structures that are resilient and can handle the unexpected. It's about anticipating potential weaknesses and mitigating those risks.
That makes sense. But with all this emphasis on safety, how do we balance that with the cost of building things?
That's a great question. And it's something engineers grapple with all the time. It's about finding that sweet spot where you're maximizing safety
without breaking the bank or sacrificing functionality. It's a delicate balancing act.
So it's not just about the science of mechanics and materials. It's also about economic realities and making informed decisions.
Exactly. It's about weighing risks and benefits. And understanding that there's no such thing as zero risk. But through careful planning, rigorous testing, and continuous improvement, we can minimize those risks and create a safer built environment.
And speaking of continuous improvement, the source material also talks about the importance of knowledge.
Absolutely.
Really understanding materials, forces, and potential failure modes. Things like the more you know, the safer you can build.
Knowledge is power when it comes to structural engineering. The more we understand about materials, forces, and how they interact,
the better we can design structures that are safe, durable, and sustainable.
It's like a never-ending quest for knowledge and innovation in the pursuit of building better and safer structures.
Exactly.
And it's not just about learning from textbooks, We also have to learn from past failures.
You're absolutely right. Every failure, whether it's a minor crack or a catastrophic collapse, provides an opportunity to learn to improve our designs and to prevent similar incidents from happening in the future.
That's a good point. We can't just focus on what we think we know. We have to be willing to learn from what we don't know as well. And speaking of learning from unexpected situations, the source material also has a section on trench shoring. Which I found really interesting.
Trench shoring is a great example of how engineering principles can be applied to protect workers in hazardous environments. Essentially, it's about creating temporary supports to prevent cave-ins during excavation work.
So it's like building a safety net, literally. It seems like a pretty high-stakes situation where any mistakes could have serious consequences.
Exactly. That's why there are strict regulations and safety standards for trench shoring. It's about understanding soil mechanics, the forces at play, and the potential for collapse.
It's a good reminder that engineering isn't just about building impressive structures. It's also about protecting the people who build them.
Absolutely.
And that safety should never be compromised. no matter how tight the budget.
Yeah.
Or how challenging the project might be.
Absolutely. Human lives are priceless.
Right.
And no structure is worth sacrificing safety for.
Yes.
It's about creating a culture where every worker can go home safe and sound at the end of the day.
It sounds like there's a lot more to consider than I ever realized.
Yeah. When it comes to building things safely, it's not just about the materials themselves, but understanding the forces at play, the potential for failure, and even the ground beneath our feet.
You've hit the nail on the head.
Yeah.
It's all about taking a holistic approach, considering all the factors that could contribute to a structural failure, and designing with those factors in mind.
This whole conversation has really opened my eyes to how much we rely on engineers and builders to create a safe environment for us.
Yeah.
We literally trust them with our lives.
That's right.
Every time we walk into a building or drive over a bridge.
That's a huge responsibility, and one that engineers take very seriously.
Yeah.
It's why there's such a strong emphasis on ethics and professional standards in the field.
It's good to know that there are people out there who are dedicated to making sure the structures we rely on are safe and sound.
But what about us?
Yeah.
The non-engineers?
Right.
What role do we play in all of this?
That's a great question.
Yeah.
We can all play a part in creating a safer built environment.
Right.
It starts with awareness.
Okay.
Paying attention to our surroundings, noticing potential hazards, and speaking up when we see something that doesn't seem right.
So it's not just about leaving it to the experts.
Right.
We all have a responsibility to be vigilant.
Exactly.
Okay.
Think about it. You're more likely to notice a crack in your own home's foundation than a structural engineer who's never been there.
That's true.
Right.
I never thought about it that way.
Yeah.
So if we see something that seems off, what should we do?
Yeah.
Should we just call 911?
Well, it depends on the situation.
Okay.
If it's an immediate danger, like a collapsing structure or a gas leak, then yes, absolutely call 911. But if it's something less urgent, like a crack in a sidewalk or a wobbly handrail, you can report it to the appropriate authorities, like your city's building department.
Okay, that makes sense.
Yeah.
It's kind of empowering to realize that we can all contribute
to
making our communities safer, even in small ways.
Exactly.
Okay.
It's about being informed citizens and advocating for safety. We can also stay informed about building codes and regulations in our communities and support policies that prioritize safety and resilience.
So it's not just about reacting to problems. It's about being proactive and advocating for change.
Exactly.
Okay.
It's about creating a culture of safety that permeates every aspect of our built environment. And that starts with each and every one of us.
Well, this conversation has definitely given me a lot to think about.
Good.
I feel like I have a whole new appreciation for the complexity of the structures around us.
Yeah.
And the importance of safety in design and construction.
I'm glad to hear that.
Yeah.
The more we understand about mechanics and structures, the more informed decisions we can make, both as individuals and as a society.
So as we wrap up this fascinating dive into the world of mechanics and structures, what's one final takeaway you'd like to leave our listeners with?
I'd say it's this. Never underestimate the importance of asking questions.
Okay.
Challenging assumptions and demanding that safety be a top priority in everything we design, build, and use.
That's great advice. It's a reminder that we all have a role to play in creating a safer world.
That's right.
Thanks for joining us on this insightful exploration of mechanics and structures.
It's been a pleasure.
And to our listeners, we hope you learned something new and are feeling inspired to be more aware of the forces at play in the world around you. Until next time, stay safe out there.